Precalculus, Module 7, Investigation 3, representing circular motion. Imagine a bug sitting on the end of a fan blade as the blade rotates in a counterclockwise direction. The bug is 2.6 feet from the center of the fan and is located at the 3 o'clock position as the blade begins to turn. What quantities might you track to represent the location of a bug as it sleeps on the tip of a rotating fan blade? List as many quantities as possible. There are a couple of important quantities that I'm going to point out. So let's say that the bug's moving in this circular motion and then he's about right here. We know that since it's circular motion, like this distance here would just be the radius, 2.6 feet. That's a quantity. It's a constant or fixed quantity. Certainly a measurable attribute of the bug, its distance from the center of the circular motion. Another really important one, though, is this vertical distance here between the horizontal. So that's an important quantity. And also this horizontal distance that the bug is from like a vertical axis. That's going to be an important quantity for trigonometry. We could also talk about the arc length, etc. Lots of different quantities there. 2a, explain how the bug's vertical distance above the horizontal diameter changes as the bug travels from the 3 o'clock position to the 12 o'clock position. So this vertical distance is the line I drew here. That's what we're kind of talking about. And let's imagine that the bug started here. Here's their initial position, and that's 3 o'clock, and we go all the way here to the final position, which is our 12 o'clock position. So again, explain how the bug's vertical distance changes. Notice that here, initially, the bug's vertical distance is 0. Vertical distance above the horizontal. And then what's the distance as the bug moves this way? What's this distance? It's 2.6 feet. So the bug's distance changed from 0 to 2.6, where it increased by 2.6 feet. Then, if the bug goes from the 12 o'clock position to the 9 o'clock position, notice that we're going to decrease in height by 2.6 feet. Then if we go from 9 o'clock to 6 o'clock, we're going from a vertical distance of 0, then down below we can call that a negative 2.6 feet. So again, we're decreasing by 2.6 feet. And then as we go from the 6 o'clock position here to the 3 o'clock position here, that vertical distance will increase by 2.6 feet. From negative 2.6 feet to 0 feet. 0 feet above the vertical or the horizontal axis. As the bug travels from the 3 o'clock position to the 12 o'clock position, how does the angle measure that is swept out by the fan blade change? So again, looking at these same initial and final points here, if we start initially at 3 o'clock and we change to 12 o'clock, notice initially, like, we don't even have an angle measure. It's really like the terminal and vertical sides of our angle are the same. Like the bug hasn't moved at all, so there's no angle measure associated with it. But as the bug moves out this way, the angle gets larger and larger until eventually we get to our final position at when the bug is at the very top here. Notice that the angle has changed from 0 radians, and up here at the top is pi over 2 radians. The way to think about that is, you know, all the way around is 2 pi radians. Halfway around is pi. Up here is pi over 2. So the angle measure has increased by pi over 2 radians, from 0 radians to pi over 2 radians. You could also say it increased by 90 degrees. Part C, for successive equal changes of angle measure from the 3 o'clock position to the 12 o'clock position, how do the corresponding changes in vertical distance change? Identify these changes on a diagram of the situation. Okay, so let's just draw a circle here. This is a kind of a tough question. It's just weird to figure out what you're asked to do, but here we have a circle. Let's say that we have a bug hanging out right here on the right side, and then we want to go all the way up here, but let's think about if we divide up this region here into parts. Like we could divide it in half, then we could divide each of those halves into halves. So we can discuss what happens if we change by the same angle measure or the same arc length. Notice that each of these little slices has the same angle measure. So the question is, what happens to the changes in vertical distance? So first of all, this first change, as the angle increases from here to here, notice the vertical distance increases from 0 up to this point here. Then I can look at the next change. So this isn't really the change here, this piece right here. The change would be what would happen when we're starting from this point right here, and then what's the vertical distance up? You see, it's really this piece right here that we're interested in. And we can look at another change starting from this initial height, and if we go from that initial height up here, and then starting from this point as our initial height, we just go up a little bit more to get to the top. So here's our first initial height, and then I'm going to erase this piece. We can see that this piece is our second change in height. So our change in height, a change in height, change in height, and then here we have another little bitty change in height. Notice that the changes in height are decreasing. The changes in vertical distance are decreasing. So how do the corresponding changes in vertical distance change? They decrease. Create a graph to illustrate how the bug's vertical distance above the horizontal diameter, measured in feet, co-varies with the measure of the angle theta swept out by the bug's fan blade, measured in radians. Plot points using the axes below to illustrate how the angle and the vertical distance co-vary. Okay, so let's say that this axis is our angle in radians, and the vertical axis can be the vertical height. Notice when we start out with 0 radians, we don't have a vertical height. So we go through the origin. That's when the bug is at its starting position. And then let's go back and look at this circle for a second. Notice that we took like the whole circle and we divided it into a fourth to start out with as we go to 12 o'clock. Then we took that fourth and divided it into fourths. 1, 2, 3, 4 pieces here. Now, I'm going to get a little bit technical. And all the way around there's 2 pi radians. So if we divide that into fourths, we get pi over 2. But then if we divide the pi over 2 into fourths, we get pi over 8. So each of these is pi over 8. Each of those angles swept out. So these are our changes in height. Changes in radians. Like we go from pi over 0 to pi over 8, then to pi over 4, then to 3 pi over 8, pi over 2. Notice that this is just 2 pi over 8, 3 pi over 8, 4 pi over 8. And we saw that at first we increased by quite a lot. So we maybe go up, increase by a bit. Then we keep increasing up to this point, but our increases get kind of shorter and shorter. And then, as we go from 12 o'clock down to 6 o'clock, those vertical heights are going to decrease back to 0. So this graph decreased back to 0. And then it's going to become negative. As we go down here, the heights are going to become negative, but the changes in heights are going to be decreasing. We're going to have something concave, actually concave up, because we're getting smaller and smaller changes, negative changes, which means that we're increasing. But in general, we're going to see something like this. We're going to come back to 0, and then this behavior is going to repeat. This is again the vertical height versus the angle in radians. And that should look like, if you've had precalculus or trigonometry before, it's a familiar looking periodic function. How will your graph indeed change if the radius of the fan is 3.9 feet instead of 2.6 feet? So notice at pi over 2, that's when my height was a maximum. So this is 2.6 feet right here is this this vertical value. Again, that corresponds to the fan because it's the radius of the fan. As we go to 12 o'clock, we're at pi over 2 radians, and that's the maximum vertical distance we can have. If the radius was to change to 3.9 feet, this whole graph would be shifted up a bit. It would start here at 0, and we would go up higher, because 3.9 feet would be somewhere up here. And the amplitude of our function would be larger. So notice that the maximum value of our graph would change from 2.6 to 3.9, and the minimum value would change from negative 2.6 to negative 3.9. Part F, create a graph to illustrate how the bug's vertical distance above the horizontal diameter covaries with the measure of the angle theta swept out by the bug's fan blade. Plot points using the axes below to illustrate how the angle and the vertical distance covary. Okay, this question is very subtly different from the last one. The difference is we want to measure the vertical distance in radius lengths rather than just some units like feet or inches. So so this axis is radius lengths. Again, it's the vertical distance, but it's the units are radius lengths. And then again here we have the angle in radians. What's interesting is it's pretty much going to be the same graph as this one, but whereas here the highest point was the radius 2.6 feet, in this case the highest point will be 1 radian. Or 1 radius actually, sorry, 1 radius. Then the lowest point will be -1 radius. That'll be the vertical distance will be 1 radius. It'll still be the same kind of graph. But now everywhere where we had 2.6 feet we have a radius, and so we're just measuring the vertical distance in terms of how many radians rather than feet. Explain why the graphs you created in part D and F have the same general shape. Essentially, we have the same quantities for each axis. The horizontal axis is the angle in radians. The vertical axis is the vertical distance above the horizontal vertical height. But we're just having different units. In this graph the units are feet. In this graph the units are radians. And so we're just talking about the same exact relationship using different units. And that relationship is a relationship between angle measure and vertical distance above the horizontal. The function you have been working with and graphing in problem 2 is called the sine function. It is given a special name because of how common the function is in math and the sciences. The sine function is classified as a trigonometric function. A function that relates an angle of rotation of a point xy on the unit circle measured from the 3 o'clock position to the distance of that point above the horizontal axis measured in number of radius lengths is referred to as the sine function. We see that an angle measure theta is the input of the sine function, and the output, sine theta, is a distance above the horizontal diameter measured in radius lengths. The sine function is often abbreviated by writing sine as the name of the function. So, yeah, when the input is the angle in radians, the output is the vertical distance above the horizontal in radius lengths. When you're talking about circular motion, this graph represents the sine function. Just a set of inputs and outputs. Label a point xy on the unit circle below, then label theta and sine of theta as defined above. So if we just pick a point, say right here, here's our point xy. Notice that all the radii are 1, so that's our sine function. Let me draw this a little bit better. So here we have our angle theta. So there's angle theta. And then sine of theta is simply this vertical distance here from the top to the bottom, or from the bottom to the top. But notice as theta changes, sine theta will also change. So as the input changes, the output, the vertical height changes. Explain how the bug's horizontal distance to the right of the vertical diameter changes as the bug travels from the 3 o'clock position to the 12 o'clock position. Again, we have our bug. It's right here on the fan plate at the 3 o'clock position, and we change to the 12 o'clock position. Now it asks, how does the bug's horizontal distance to the right of the vertical diameter? So here if we have a vertical diameter, and then this is the horizontal distance right here. Notice that the horizontal distance starts from the radius, and then as we go up to this point here, there is no horizontal distance from the vertical diameter. The vertical diameter is 0. So the bug's horizontal distance decreases from 2.6 feet to 0 feet. Then if we go from 12 to 9, notice we have a 0 for our... Notice that we start at 0, so the bug's distance horizontal, it's going to change from 0 feet, and then we are 2.6 feet away from the horizontal or from the vertical when we're at this position right here. But notice if we call this direction positive, if we call positive to the right, then we're going this way, we're negative. So this distance right here, we could say is negative 2.6 feet. So the bug's horizontal distance is changing from 0 feet to negative 2.6 feet, which means that we actually decrease by 2.6 feet. Then as we go from 9 to 6, we are from negative 2.6 feet to 0 feet will be our horizontal distance from the vertical. And so there's an increase of 2.6. Then if we go from 0, or from 0 feet here, we'll go to increase to 2.6 feet. That's from 6 o'clock to 3 o'clock. We have another increase by 2.6 feet. For successive equal changes of angle measure from the 9 o'clock position to the 3 o'clock position, how do changes in horizontal distance change? Identify these changes on a diagram of the situation. So if we go here, our initial point is at 9 o'clock. Then our final position here is at 3 o'clock. Let's break this down. We could break that whole angle from here to here in half. Then we could break it up into, say, fourths. So now notice where if our angle increases by this amount here, how does the horizontal distance change? We start out with the horizontal distance equal to the radius. Then we end, and this is our horizontal distance. Notice that the change in horizontal distance is actually, see if I can show this to you guys, if this will stop changing. Notice if we start right here at the final point, we can clearly see that the horizontal distance that we've changed by is just right here in green. So there's that initial change in horizontal distance. Then if I go from here to here, like if I go from this point to this one, then we see the change in distance is this line here. Next, if I go from this point to this point, we have a similar change in distance. But then that final change in distance is actually very small, this purple distance here. Notice that we're changing by the same angle amount each time. And first we have this pretty small change in distance, but then there's a larger change in distance, and then there's another pretty big change in distance, then we have a small change in distance again. So notice that what's happening, the changes in distance increase, but then they start to decrease. create a graph to illustrate how the bug's horizontal distance to the right of the vertical diameter. Notice it says to the right. That means we're positive if we're to the right and negative if we're to the left. How that distance co-varies with the measure of the angle theta swept out by the fan blade measured in radians. Notice that if we start with our fan in its initial position, that's not the fan. Then it's already at its maximum distance, its radius. So this graph, instead of starting at 0, like with the sine function, we're going to start up here. Let's say this is 2.6 feet. And then as we go from 3 o'clock to 12 o'clock, remember that the horizontal distance decreased to 0. Then it became negative, and it went back to 0, and then it increases again. This is going to be the type of graph you'll see. It says the function that you've been working with in graphing in problem 4 is called the cosine function. A function that relates an angle of rotation of a point xy on the unit circle measured from the 3 o'clock position to the distance of that point to the right of the vertical axis measured in number of radius lengths radii is referred to as the cosine function. We see that the angle measure theta is the input to the cosine function, and the output cosine theta is a distance to the right of the vertical axis measured in radius lengths. The cosine function is often abbreviated by writing COS as the name of the function. Label a point xy on the unit circle below. So here's a point xy. Then label theta and cosine theta as defined above. So here's theta. Then cosine theta is just that vertical distance here. Horizontal distance from the vertical diameter. This little piece right here is cosine theta. You could see it down here. Notice that cosine of theta equals x. Another interesting thing that you can notice is that sine of theta equals y.